but you should come up with at least a page of different things with diagrams, drawings, and ideas of how you could use them in different ways, creative uses of these things. I don't want it to become a outrageous list. For example, a piece of paper cannot be used as a parachute. I want it to be practical things. If I picked up a piece of paper right now, I could use this piece of paper to do it. I wouldn't have to have any extra junk. I wouldn't have to do anything outrageous or crazy. I'd just be able to use it for doing these things. And then number 4, which is how could you keep raindrops from blocking the view through a windshield without using squeaky windshield wipers? And it says to list 5 ideas. Again, this list should include diagrams, should include details, and so this list could take as many as 5 pages if you list 5 ideas. A page could be an idea that you have. You write down the idea, you explain some of the details about the idea, you make a diagram or two. You know, I mean, these ideas should be in detail, okay, for this homework block. Detail, detail, detail about how you would implement those 2 things and those 2 problems. So, think like NASA does. There's a great picture in this book on page 137, which I will show you right now. So let's think like NASA. Why is NASA considered pretty creative in their thinking? Oh my goodness, it can't focus. Focus already. Where's my autofocus? I don't know where my autofocus is. Focus. So, why is NASA creative? They see this thing that's connected to NASA. Guess where the door is for the space shuttle? That's where it is. Right where that thing's connected, essentially. And so, I mean, you have a space shuttle. It's going to go into space. You don't care where the door is. And so where do they put it? They just put it on the top above the cockpit. So you walk into the space shuttle on Earth, space shuttle's standing up, and you walk into it, and up above your head is the cockpit. You have to climb into the cockpit through a ladder. And when you're sitting in the space shuttle, of course you're actually laying down when it's on Earth. But in space it doesn't matter, and so they just went ahead and put the door where it was convenient. Turned out the door was convenient to go through the roof of the space shuttle. And so they did that. NASA is replete with examples of being creative because they know what situations they're going to be in, and they know what matters and what doesn't. So, I'm going to try not to talk too much today so I don't blow my voice out. There's allergies going around in my house. Don't want to. Everybody in my house has serious allergy problems right now. Not sure if it's because of something local to my neighborhood, but apparently everybody's getting them, not just me in my house. But anyway, we're going to do section 5.1, and we may get all the way through, we may not get all the way through it. Section 5.1 is dealing with what we call the engineering design method. And I'm going to show you what they have on their second page of this chapter. It's a chart here. We're going to come back to it in a minute. Let me zoom out here a little bit. This chart is what they're calling the engineering design method. And you can see that it's got lots of boxes with words in them and arrows going all kinds of places and some labels in it. We're going to look at that in great detail. First thing that I want to look at, though, is this page here, the first page. We have essentially 4 elements of design. We'll zoom in here again so you can see if you don't have your book with you. The first element of design is synthesis, right? The second one is analysis. The third one is communication. The fourth one is implementation. So synthesis essentially meaning bringing things together. Your analysis is essentially to figure out what's going on or what's not going on. Communication, I think that's pretty obvious. You're going to have to write about this, you're going to have to talk about it, you're going to have to communicate it. And then implementation is actually doing the thing that you're designing, doing or applying it or whatever. It's not that complex here, but it does get fairly complicated in real life and practice. And so what we're going to do is we're going to look at the engineering design process as it is demonstrated by Google. We're going to go to our... Anybody know what Google, the word Google comes from?
Pretty sure it means about a unit of numbers.
What's that?
Is it like a unit of numbers, like billion, trillion, but it's a lot higher than that?
The Googleplex is where Google comes from, and Googleplex is a big number. It's 100 to the 100 power. It's pretty big. Yes, so that's why they used that for the word Google. I'm going to search images, the images here for the engineering process. And we can see here that we get lots of these processes that come up. But what do we notice about these things? Most of them have kind of a similar format to them. What is the format of most of these engineering processes?
Circle.
Yeah, there's some kind of circle or cycle, right? There's something that is repetitive about them. The circle is this great shape that always comes back around to itself. This has that great shape that comes back around to itself. This one does too, this one does. It's, the engineering design process is often demonstrated as a cycle, right? So why would we demonstrate the engineering process as a cycle? Is the engineering process ever complete?
No.
Are you ever done engineering something? Are you ever done figuring out something? We're never done. There's always something more to be done. There's always something to be changed, to be fixed, to be altered, to be improved, to be repaired, right? There's always something to keep the process going. So the engineering process never really ends. In fact, there's one engineering process that began thousands of years ago and is still continuing. It's still, the process is still rolling forward. And rolling being the key word. What is that process? The process is the invention of the wheel, right? We have invented the wheel so many times, but we never really got out of the idea that the wheel is round and it's designed to roll and something is going to be on top of it, right? And so we talked about that earlier in this class when we were looking at the history of engineering. We looked at the invention of the wheel, right? But of course the wheel has come a long way. If you look at, for example, if you look at the wheels now that we're making, they're still round, like they used to be, but the materials they're made of, the shapes that they are, the interior workings of these things are way different. Here's a classic, not a classic. Here's a pretty strange example of this. We have a wheel that's made of carbon fiber here, and we have these three, for lack of better words, spokes that are actually kind of rings inside of here, made of carbon fiber as well. And it turns out, actually I'm not sure about these ones. These ones could be one single piece for all I know. But you have this incredibly complex wheel design. It's extremely different than wheels that were made even 10 years ago. It's an electric bicycle wheel. And then we have wheels like this that are on newer cars, also made of fancy materials, carbon fiber. We have a car wheel like that, a motorcycle wheel like this that actually has, instead of a bolt pattern on it, it has a single connection in the middle. Wheels are getting pretty far out there. Let me see if I can find, here's one of my favorites, bicycle wheels. So this bicycle wheel is made completely of carbon fiber, and instead of having spokes, it has blades. This is getting pretty crazy, this stuff. So the wheel is one of those engineering processes, engineering designs that's still going on. We're still improving it, we're still modifying it, we're still changing it, even though, you know, it's still round, it still rolls, it's still connected to something that is bearing the load. And when I was a kid, I took my bike apart all the way down to taking every last bearing out of the hub of the wheel and repacked the bearings with new grease. I built my bike up from scratch. I must have been 8, 10 years old, I don't know how old I was, not very old. So I could learn about these things. And since then, the wheels have changed to the point that you can't even take them apart like that anymore. The bearings are sealed bearings in a sealed kind of cartridge, I guess you call it, that just snaps into the wheel, and the cartridge is literally welded together, and you can't really take it apart. They're sealed up so that the grease doesn't come out, so you don't have to repack the grease. So you got lots of really interesting things going on in the engineering process today that have been going on for thousands of years, this cycle that just keeps going. However, these circular ones are not the ones I prefer. These circular ones kind of imply that there's a next step, and then a next step, and a next step, and a next step. But that's not always the case. Sometimes you gotta skip a step. Sometimes you gotta skip back a step. So the arrow going from one to the next doesn't really fit the engineering process to me, because sometimes you get somewhere in this process, and you'll run into a roadblock. You'll have some kind of hurdle that you just can't get over, and you might have to jump back to another step and redo a few steps. Or in some cases, you might have to skip forward to a step. It happens less often, but it does happen. Sometimes you have to start the whole process over again. So you have to have some kind of mechanism for dropping out of the process and jumping back in. And that's where you get to some of these processes that look maybe like this one, where you have these things that go in between the steps in the middle, or this one over here, where there are places that you can go from step to step to step, but there are also places where you can jump out and go back to a particular step. Or you can get a little more complex and have these diagrams that have places you can go all over the place. You can go back, you can go forward, you can retrace steps, you can move back and forth whatever way you want to, whatever way is necessary. And that is more like the one in our book. So let's see if we can find another one that's kind of like the one in our book, one that's easy to understand. There are lots of these processes that are quite good, I think, but some of them are much more difficult to understand than others, as far as understanding how they built the process. Well, let's look at this one really quick. So in this case, we have a solution at the beginning, or a request for a solution. We identify some inputs, and we go down to this engineering design solution here. And here they're talking about particular products that they're going to use to design with. They're going to design with SolidWorks, which is a computer program. And we come down here to, we know what DFMA makes, and then we have probable drawings, and we go around this loop. But you can see here that there are arrows where we back, there are arrows where we can skip forward, there are arrows where we can jump out, right? And we, this entire bottom half of the process is a process that you can get stuck in a loop, where you can be creating solutions, the solutions don't work a particular way, something fails, something doesn't meet qualifications, so you go back and you redesign, you revisit the problem. And that is probably the most important part of the engineering process, is this ability to analyze what's going on, to decide whether or not your design or your process is meeting the goals of the process, and then to go back if it doesn't, or to go forward if it does. There's another one that kind of has this idea here, where we have the problem at the beginning, but you can go down through this process on the right side. You can go back up through the process on the right side. You can jump up through the process on the left side. So there's all kinds of options for going backwards and forwards through this process until you get it right, until you get it right enough. So let's take a look at, in particular, our process in our book again, and let's see what we can see. Okay, so this is the design process in our textbook. Starts up here at the top with identifying the need and defining the problem, right? In engineering, that's what we're all about. We're all about saying, hey, what's needed out there? What is it that what problem we're trying to solve? And in that particular part of this process, it's not just, hey, we need something to pick up, to pick berries off of a plant. That's too general. We need specifics, okay? So we're going to get specific, more and more specific as we go through this process, and we're going to create something that is very specific to what we want. We also want to define the need, identify the need, and define the problem in writing. That means in writing words, that means in drawing of diagrams if we need to, that means in the taking of pictures if we need to. We need to define this problem on paper somewhere, or at least on electronic paper, right? So identifying the need and defining the problem is not just an idea in our heads. It's not just a pie in the sky. It is, there are juniper berry bushes in North Platte, and the farmers in North Platte want a machine that can be towed behind a tractor and can pick these berries without ruining the plants. That is identifying a problem, identifying a need, okay? And you could even go a little more specific if you needed to be, but that'll do for now. Then we've got our second step here, which is to assemble a design team. So if we're going to pick juniper berries, who would we maybe put on our design team?
Mechanical engineer?
Mechanical engineer. Picking berries is probably a mechanical process. You're probably going to have something that mechanically removes the berries from the bush, probably, right? So we're probably going to have a mechanical engineer. What else?
Food engineer?
We might have a food or an agricultural engineer, probably an agricultural engineer, right? Or somebody in agriculture. Could even be the farmer, right? They've probably done their fair share of picking juniper berries, probably know the process, understand the berries. So we want to know somebody, that really understands what's going on out there. And they don't necessarily need to be an engineer. And it's probably your client in this particular case. Not always is it the client, but oftentimes it is. But your client is probably your design, not necessarily for all the nitty-gritty and the everyday stuff, but they'll be there at the beginning. They'll be there a few times through the process to make, so that you can bring your ideas to them, to make sure that you're meeting their needs. So the client, the client definitely is part of the team. They're paying for the project after all, right? Who else? Maybe some other engineers? Are there any machines out there that don't use electricity of some kind and a computer of some kind anymore? Not many, right? Most of these things out there are going to use a computer, or they're going to use some kind of electricity. So you probably want an electrical engineer on the job. You might want to have a systems engineer if this becomes a very, very complicated process. You want somebody to organize the process. You might want to have a manufacturing engineer, because if you're going to develop a product that's going to actually make money, you need to know if it can be built at a decent price, right? So you might have several kinds of engineers. It depends on what you're trying to do. But your design team is definitely going to include some technical people, some engineers. It's definitely going to include some experts in the field that you're trying to solve the problem in. Probably in this case, a farmer, a client, somebody like that. What else? Who else are you going to have on the team? We've got technical people, we've got experts in the field we're trying to work in. Who else? Who's going to sell this thing? The engineers like going out and selling things? No, they want to get out and make things. They don't want to sell things. Some engineers do become the sellers of things. Usually they're the ones that enjoy the selling more than the making. And that's fine. There's nothing wrong with that. But you're probably going to have some kind of sales, some kind of marketing something team, right, on your team. Somebody that's in charge of that, or a group of people that's in charge of that. So you're going to have marketing people maybe on your team. And you say, well, they're not really on the design team. Well, absolutely they are. Do people who sell things know what sells? Absolutely. Okay? Absolutely. The saying in the world right now is that sex sells, right? That applies in so many things you wouldn't even begin to understand. They try to allure people in with alluring images, even though they're not directly sexual images. They're appealing enough to the human psyche in that way, in that kind of primal way, that it is almost kind of sexual. Okay? And that is something that has been discovered by marketers and has been utilized by marketers for 100 years or more. Okay? Go look 100 years ago at the Coca-Cola signs. Who's selling the Coca-Cola on the sign? Man or a woman? Woman. Beautiful woman. Nicely dressed. End of story. It is. That's how it's done. Okay? So, it's... they know, marketers understand selling more than engineers do generally, and it is definitely a kind of a science. And if you want to sell something, it needs to look great. There are plenty of cars out there that don't sell well because they look like crap. They look terrible. Chief among them was the Toyota Prius. You know how badly that car sold when it first came out? Because it's so stinking ugly. And now, people have gotten used to it, and they actually like the shape of it. And so other cars are shaped like the Prius, because it's like somehow equated with being responsible or something for the climate, right? But it is definitely, image is definitely something that is important in selling. So you got to have people on that team that are literally part of the team that are going to make it look great. Even tractors nowadays look great, don't they? I mean, come on. You know, the tractor back in 1938 looked like this. It had a big box on the front, had a seat that sat up here, and a wheel this big and a wheel this big, and that was the whole thing. And ugly as all heck. The only people that find those beautiful are farmers that collect tractors. They're just ugly. Just ugly, ugly, ugly. Nowadays, you know, the newest case tractors, or they have this shape to them on the front like this, and this cab that's all race car looking, and you know, the wheels are almost hidden. They're still huge wheels. They're bigger than they ever were before. But they don't seem as big because the tractor in comparison is bigger. Even though you don't need all that space in there. Most of that space in there is empty space. It's just a big old shell. Right? But they still do it. It's still very important. There may also be other factors involved that you may have to consider. Even though we're building a machine for picking berries, there may be other factors involved. For example, with tractors today. Have any of you ever been in the cab of a tractor today? One of these modern tractors you have? What's it like in there?
Lots of electronics.
Lots of electronics. Is it comfortable?
Very comfortable.
What's the seat like?
Lots of suspension.
Ergonomic is the word, right?
Yeah, there you go.
The seat, it's like sitting in your favorite seat. It's so comfortable. What else is in there?
It's got a GPS system.
GPS system. Does the guy even have to drive?
Nope.
No, he's just there to push the button. He's there just in case the thing breaks. Right? They're not allowed to sleep in it, but they can do it. What can they do while they're in it?
Listen to the radio.
Listen to the radio, which is usually a top-end radio, like an Alpine with great JBL speakers. Okay? What else can they do? They can watch movies in some of these. Some of them have like DVD players. Some of them have Netflix you can download directly into the cab. I mean, they have everything. And when they turn on these tractors have huge turbo diesel engines. Turbo diesel means that it has a huge turbine inside the engine that recompresses the air, the hot air that comes out of the engine back into the pistons so that it preheats and pre-compresses the air so that you get much more power and efficiency out of your engine. That turbine is really loud and really high-pitched and annoying. Can you hear it when you're in the cab? Even though the cab is made mostly of glass, you can't hear it. You know why? Because some acoustic engineers, some of which I know, I met some of these guys when I was at school, actually, because they do this at BYU. They actually were able to create a sound system for Caterpillar tractors that's used in Case tractors and other tractors all over the world that actually actively cancels out the noise. It records the noise that the engine is making, or it has a microphone that is listening to the noise the engine is making. That noise is put into a computer program, an algorithm, that creates that same noise, but with the opposite amplitude, so that the noises cancel out when you're in the cab. So it just erases that high-pitched noise. High-pitched noises are the most obnoxious to most humans. There is a certain frequency range of low-pitched noises which are kind of annoying. You can hear one in this room, it's kind of like, right? Those really low-pitched noises where you can hear each individual wave are extremely annoying to humans, but very difficult to cancel out. But those high-pitched ones really drive humans crazy and give them headaches. And a lot of headaches, for example, in the office place are due to those high-pitched noises in computers, those fans in computers. And they're starting to put these same ideas into computers. So this has nothing to do with picking berries. We're picking berries. But there may be considerations like that. So it's always good to find those things out and to include somebody on your team. You may not find that out till later on in the project. But if you do find something out later on in the project that is going to be that should be part of your project, you may have to bring somebody else into your team. Okay? Now there's something that's really important about assembling a design team we haven't talked about here. Who's going to pick all these people? It's like chicken and the egg, right? Who's going to pick these people? We're going to have a leader. Right? So assembling a design team is going to be, a big part of that is going to have to be a leader is going to have to be in charge of all this, right? So, after we've got our design team together, we've identified the need, we've assembled our design team, number 3 says that we're going to identify constraints and criteria for success. This is where your client is going to play a huge role. Your client is going to sit down, and all the technical people are going to sit down, and all the marketing people are going to sit down, and the client's going to say, this is what I need. And then the technical people are going to say, well, what does that mean? Right? He's going to say, I need you to make a machine that picks juniper berries. And maybe the mechanical engineer says, what the heck is a juniper berry? Because they don't know, right? And they want to say, maybe they want to say, well, what size are they? How far do they grow from the ground? Are they a soft berry or a hard berry? Are they round? Are they long? Are they whatever? What are the challenges that you have now collecting juniper berries? How many of them will you collect? How far apart are the bushes? How tall are the bushes? Where on the bush is the berry? Raspberries, for example, grow underneath the branches, underneath the leaves, right? Whereas other kinds of berries grow in between the leaves or on top. You got to know a lot of these things, and so in this process of identifying constraints and criteria, you're going to find out what it is exactly you need to do so that you can figure out exactly what you're going to have to design to do it. In the end, when you get out of this process, you're going to know exactly where those berries are, how hard it is to pick them by hand, what other methods they might use for picking them, and the measurements of the berries, the measurements of the trees. You're going to have lots and lots of details that are going to help you to do step 4, which is to search for solutions. You have to have those details so that you can find solutions that will actually fit the criteria and the constraints of the project. Right? At the end of this step 3 here, you're going to have essentially a list of things that your machine must do, and they're going to be specific things. This machine must move at 4 inches per second. This machine must be 4 feet wide so it can pick berries on both sides of the row. This machine must pull the berries off from below the branch. This machine, you're going to have lots and lots of things. This machine, and it's in everything that you've listed is going to have specifics. This machine must not apply more than 1 pound of force to any particular berry. This machine must sort the berries from the whatever, you know. So you're going to have very specific things listed at the end of that process where you are identifying the constraints and the criteria for success. And then that list is going to be used to search for solutions. When you're searching for solutions, you're going to prioritize your list. You're going to make number 1 priority is that it picks the berries from below the branch or something. And the number 2 priority and number 3 priority, you're going to rank them and you're going to score them. And then you're going to come up with possible solutions and you're going to plug them into this criteria list and say, how does it fit the list? How does this idea, this possible solution, fit these criteria? And you're going to use those criteria that you created in step 3 and the solutions that you come up with step 4 to find the best solution. Now, of course, we've done this, haven't we? We did this with our bridge. 24-inch bridge, 20 pounds weight, right? Well, we didn't say 24-inch bridge. We said it had to bridge a 24-inch gap, right? So we gave our constraints, our criteria. Of course, your design team was just you, yourself, and yourself. And then searching for solutions, you went online, you looked at different bridge designs, maybe you used the bridge builder online, whatever you did. And then you ranked those solutions, you ranked those ideas, and you built the one that was best. And then you tested it, and you fixed it, and then you tested some more. These 4 steps at the beginning are called the synthesis. That's the part of it which is synthesis, where we are going to come up with the problem and come up with the beginning of the solutions. The second the second set here, steps 5 and 6, are synthesis and analysis. They're kind of a crossover between synthesis and analysis, where we analyze the potential solutions and choose the best one, and we start to go through now a cycle here. We come down from our search for solutions, and we've got maybe 5 different possible solutions. We go through a feasibility study to decide which one is the best. We analyze them each, and then we go through this process where we might go back up. We might come back up to here at some point in the preliminary design or detailed design. So we start to see this process. We're going to come down through here, analyzing possible solutions, choosing the best solution, and then we document the solution. When we document the solution, we start putting the solution together on paper. We start drawing pictures. We start making lists of materials. We start making prices, looking at prices of materials. And then once we've got that documented, then we bring it to the management. We bring it to whoever's in charge. Usually what you do is you bring it back to your team. Right? You bring it back to your team and you say, here's the solution that we came up with. Everybody comes up with some solutions, and maybe you do it as a team. But then you come back to the team, and maybe that goes through management of the company. Maybe it comes to the client, whatever. It comes to somebody for approval, and maybe it doesn't work out. So you have to come back up here and choose a new potential solution, right? And then you go through this process again. Maybe it doesn't work out, and you come back up through here again. And finally, when you come up with a design that on paper and in our minds and with our computers is working out, then we go through this one last time and we put in all the details that we need, right? Details being, well, we're actually going to make this out of this particular metal. We're going to make this with this particular gear made at this company. And you do this one last time, putting in all the details, so that when we're done, we know exactly what we're going to do to build our solution. So we build our prototype. Here we're constructing the solution, and once we've constructed it, then we analyze it again. So this is implementation. This stuff is analysis. This is communication. Implementation is where we build this model of this thing, and we're going to test it. We go down to analysis again, and we may end up going back to the very beginning. We may end up going back to here again. That can happen as well. But there is this possibility of going back and starting again at some point in this process, anywhere in this process. So the engineering design method, honestly, is really quite simple in its idea. We're going to come up with some ideas, we're going to have a problem, we're going to come up with some ideas for solving the problem, then we're going to choose the best idea, then we're going to implement that idea. Simple, right? But you can see that it gets fairly complicated when you start to realize what the real world is like. We will meet with challenges, we will meet with roadblocks, we will meet with major problems. And we have to have an organized and structured method for dealing with those problems. Every time you go through this middle part of the process, notice that there's going to be a documentation. At the end of an engineering process, you may end up with 50 different drawings or 1 million different drawings of your design. If you go talk to any architect or any builder and ask them how many blueprints that they've received from their engineer over the course of a project, you'll be astounded. 30, 50, 100, every one of them different. Why? Because this process goes on during the building process as well. They meet a problem, they come up against a problem, maybe they're running out of money and they need to finish the project with less money than they started with. Maybe they found that the ground in one portion of where they were building is softer than the rest of the ground, so they have to re-engineer that part of the foundation. Maybe they found the materials from the company that they bought their materials from are inadequate. So they either have to order from a different company or order a different material from the same company. And they have to redesign, redesign, redesign. Happens all the time. There are so many examples of that. So you are going to have to do a lot of writing. And this frustrates my students more than anything. They say, I came to engineering to get my hands dirty. I want to build things. Sorry, that's not what engineering is about. You'll get your hands dirty plenty in the real world of engineering. But learning engineering is not about learning how to do things with your hands. It's about learning except for writing. Engineering is right here. It's in the documentation and the communication. And using that to understand what's going on. And then redesigning and doing it again and again. 90% of engineering is done on paper and on computers. So, and it's different for different types of engineering. In some engineering, it's actually really easy to prototype. Electronics is an example of that. In electronics, you can prototype a circuit board in your shop, which most electrical engineers do. You can prototype some electronics in your shop in a day. So when I was working as an electrical engineer, we would prototype a circuit board in a day, and we'd just test the thing and see if it worked. We wouldn't even do any analysis. We'd just plug it into the machine, and if the thing blew up, which sometimes it did, then we'd just do another one. Sometimes we built them so that we could switch out the parts. We had an op-amp that was constantly exploding in our electronics because it was dealing with some high voltage on one end of the circuit board at 30,000 volts and low voltage on the other end, 5 volts. So you have this 30,000 volt difference across this circuit board. And the op-amp just couldn't deal with it. Every once in a while, I just got this zap of lightning across the board, and the thing would just mushroom out and explode and be smoking. If you ever let the smoke out of a microchip, it won't work. You got to keep the smoke in. Never let the smoke out of your electronics. That's what keeps it going. Electronics work on magic smoke. Anytime they smoke, the smoke has come out, they'll work. But anyway, well, electrical engineering. So anyway, the design process, hugely important because what it does is it saves us pain